Hello everyone, welcome to VLSI Career Craft. This is Monica. So in the previous video we have discussed the importance of pipeline architecture and we have seen how to increase, decrease, setup and hold time for the flip-flops. Uh, and we have seen the importance of timing analysis as well. Now in this video we'll see the step-by-step derivation of setup and hold timing checks for the register-based design. So let's get started. So first, let's start with the derivation of setup timing check. And here we have a synchronous design. We have launch flop, capture flop, and the combinational logic in between. So the expectation is like this. We have a data X, which need to be launched at time T launch, and it needs to be captured at flip-flop 2 at time T capture. So it needs to be launched at this edge, and it needs to be captured at this edge. So we initially have data launch and data capture times like this, and going forward we have so many delays which comes into picture, and we'll see how this affect the data launch time or data capture time, what are the extra delays and all. Now let's say we have a buffer which contributes the delay of T launch latency is added in the launch clock path. So how this affect the waveform? It contributes this delay of T launch latency. So the data launch time changes like this, T launch plus T launch latency. So here, after the data is launched at D flip-flop, it takes certain time to go to the output of the launch flip-flop. So there is a delay term which comes into the picture, which is T clock to Q delay. So how T clock to Q delay is calculated in a flip-flop, we have seen in the first interview concept video. Please look into that for the detailed explanation. So yeah, here there is an additional term T clock to Q. Now, data is at the output of the launch flip-flop and it needs to travel through this combinational logic to reach the capture flip-flop. So what is combinational logic? It is nothing but the combination of all the logic gates, and each logic gate takes certain time to give the output because it charges or discharges, and we have the rise and fall times coming into picture. So each logic gate contributes certain delay. So let's see the effective delay of the combinational logic is tcom, and this delay is added to the delay part of this equation. So we have the additional delay of tcom. So going forward, our data is now at the output of the combinational logic. So here, as we have discussed, the data should appear at the capture flip-flop certain time before the clock edge. That is nothing but setup time. So we have a setup time at the launch edge, and data should reach before this time. So the data capture time is like this. Initially, we have assumed that data should be captured at T capture, but taking setup time into consideration, we need to get the data at the time T capture minus T setup. So let's say there is an additional buffer in capture clock path as well. So how this buffer is affecting the equation? So we have the capture T capture latency that is coming into picture. So here we have this T capture latency getting added to the data capture time. So now we have considered all the possible delays that can come into picture in the synchronous design. So right now we need to derive the equation to make sure that there is no setup violation. So how do we avoid setup violation? If we make sure that the data is coming at the right point, that is before T setup, if the data arrives, there is no setup violation. So we can write the equation like this. Data launch plus the delay in the design, that is T clock to Q plus combinational delay, should be less than or equal to the data capture time. So we get this equation. How do we simplify this? T launch minus T capture is nothing but the clock period of the the clock period of the design. Let's say that is T clock. So we have a certain latency in the launch clock path and certain latency in the capture clock path. So capture latency minus launch latency is nothing but clock skew. We will discuss the concept of clock skew in detail in further videos. So what is the equation now? The final equation of setup time is T clock to Q plus T combinational plus T setup should be less than or equal to clock period plus clock skew. Often this equation is used to calculate the minimum clock period at which design can work without any errors. So now we have the setup timing check equation derived. So let's see how we can refine it more further to consider the worst case in the design. So let's have we have two cases where T clock to Q and T combinational delays are minimum and T clock to Q and T combinational delays are maximum. So let's calculate the setup time frame in both the cases, and whichever case has a lesser time frame, that can be the worst case. So in the first case, the setup time frame is like this, and the second case where we have maximum clock to queue and combinational delay, the setup time frame is decreasing. So we can conclude that when the delays are maximum, it is the worst case, and we need to consider this case for setup timing check. So the delay, we need to consider delay max. So when we substitute in our previous equation, we can get the final equation like this: T clock to Q maximum plus T combinational maximum plus T setup should be less than or equal to T clock plus Q. This equation gives the more precise clock minimum clock period or frequency of the design. So now let's derive the whole timing check of the equation. Let's say two data x and y are coming one after the other in this design. So we have two clock cycles to observe how the data is launched and how the data is captured. So we have already defined the whole time, that is nothing but the certain amount of time data needs to be held stable after the clock edge arrives at capture flop. So here X, let's say X arrived at flip-flop 2 at this point. So it is just arriving and it is waiting to be captured. And Y is arriving at the second clock cycle. So we need to make sure that X is properly captured by the capture flip-flop before Y arrives. So at this point, the X is captured, and after certain delay, if you see here, after certain delay Y has arrived. So in this case there is no overwriting of the data and there is no corruption of the functionality. But in case Y arrives before this point, X is not captured and Y is captured, so first data is lost. So we need to make sure that the time at which Y is arriving should be greater than the time at which X should be, at the time till which X should be held stable. That is nothing but the T launch latency plus T clock to Q plus T combinational should be greater than T capture delay plus T hold. So as we know, T capture latency minus T launch latency is nothing but skew. So the final equation is like this: T clock to Q plus T combination delay should be greater than skew plus T hold. So now let's refine this whole timing check equation by considering the worst case. What is the worst case? Let's say we have minimum delays in one case and maximum delays in other case, and the case which is giving a shorter time duration, like shorter whole time frame, will be the worst case. So in the first case, like when the clock to Q and T combinational delays are minimum, Y is arriving a bit early than the case where the combinational and T clock to Q delays are maximum. So the time whole time frame in first case is this and whole time frame in second case is this. So here we have a lot of margin for the for y to arrive. So this will not be the worst case. We have first case where the clock to queue and T combinational delays are minimum as worst case, and the final equation can be written like this. The delays of both the delays minimum should be greater than Q plus T hold. So I hope that you have understood clearly the derivation of setup and hold timing checks. So we'll discuss one more interview concept in the next video. Thanks for watching. Happy learning.